Welcome everyone to 264A, Automated Reasoning. I am your instructor, Adnan Darwish, and our TA for this section 1 is Meet Taravia, and he's just next to me. Can you say hi, Meet, so that people can recognize you?
Hello everyone, I'm Meet.
Right. So we are, of course, doing this over Zoom, and I just wanted to quickly go over some of the protocols we'll be adopting here before we get started with our discussion. So the class will be based on a combination of whiteboard and slides. And when I'm writing on the whiteboard, I do have a big monitor sitting next to me. It's like a 22-inch, which is separate from the monitor that you're seeing me through now. And when I do that, once I start writing, I will turn my camera off because it wouldn't capture anything interesting. So, which also means that the chat box and other Zoom controls are sitting on the other monitor. So I can't see your chats real time when I'm writing because I'm looking the other way. What I'll try to do is occasionally after every segment, basically go to the chat box, see questions, and then answer them. We're following the UCLA recommended protocols about things. So that includes chats go to me directly privately. So when you send chats, only I can see them. Even Meet cannot see them. So if there is something that where you really need to interrupt and ask a question, you can raise your hand. And Meet will see that and then can unmute you. And then we'll deal with the question. But otherwise, our main way of answering question, at least initially, will be that I will be occasionally looking at the chat and see your questions and then address them. We'll start that way. These are the recommended procedures by campus to keep things under control. We used them in a class I taught last spring. It was bigger, had 200 students. They worked well. Maybe now we have a smaller class, so we'll probably relax these a little bit as we go on, but that's basically how we're gonna get started. And again, according to this setup, everybody's muted by default upon entry. So let me see. Yes, that's basically the general procedure. So what we'll do for today is basically start off a little bit by motivation on the course and what it's about, what we will be studying, and in terms of foundations, in terms of applications. And towards the end of that segment, I'll tell you more about the course logistics in terms of what's expected, in terms of requirements and backgrounds and so on. And then we will get started with our first technical discussion immediately after that. All right, so I'm going to go ahead now and basically turn my camera off and just get started with the motivation of the course. And then just before we start the technical material, we can probably go over some questions or any clarifications that people may have. Very good. So this is our course on automated reasoning, and to motivate the material of this course, which is largely it's a course about logic and its applications, and in particular the applications at least in this offering will be mostly to probabilistic reasoning and machine learning. Before we go over this, I wanted to basically talk a little bit about the history of AI briefly, because you'll see that the role of logic has evolved. And what we're doing in this course is a little bit more of the modern way of approaching logic and its applications. So we can put in context what's going on here and how we're going to use logic and what we're going to study about it. So you can think of what happened in AI as having gone through different phases. The very first phase was actually all based on logic. So from the 50s, when people started doing AI and invented towards the late 50s, the term artificial intelligence, which was coined by John McCarthy, who's one of the main promoters of logic at that time, you'll see that for decades, actually, everything was pretty much based on logic and logical reasoning. At that time of AI, the focus was on reasoning. And the idea was if you're going to build a reasoning system, it will have basically to have two components, knowledge, what we know about the world, and then you may want to think about this, about a reasoning engine that operates on that knowledge to draw conclusions. So we're basically, people were trying to model, how we think. And from the early days, the proposal by basically John McCarthy was that we will express knowledge using logic, and in particular something known as first order logic. Later people focused on what you may want to think of Boolean or propositional logic, which we will be focusing on in this class. And this was mostly something known as logical deduction. Now, this went on for quite a while, and towards the late 70s, early 80s, people have started to see limitations. The most crystallized notion of limitations was at that time that some aspects of human reasoning are not captured by logic. There was a lot of discussion about the fact that logic is monotonic, while human reasoning is not. We will actually know very technically what this means even later today. But think about it this way. In logic, if you have some knowledge base and you draw some conclusions from it, then if you add more to the knowledge base, you cannot invalidate conclusions. You can only draw more ones. So today I'm thinking I'm going to finish certain things by the end of the lecture. If network interruption happens, then that conclusion goes away. Okay, this is not monotonic reasoning. What happened here is by adding a piece of knowledge that there was a network interruption, a conclusion was withdrawn, and basically logic cannot capture that. There was basically about a decade of work on trying to deal with that. And then towards the basically early 80s, people basically start going into probabilistic reasoning as a way to deal with that. And that basically led to the discovery of things like Bayesian networks, which we will actually talk about also in this class, and more generally the notions of probabilistic graphical models that include Bayesian networks as a special case. And that was kind of a new era. Actually, Professor Ida Pearl from our department was the main driving force behind these efforts. And he had this influential book in the late 80s on Bayesian networks. And in these, the idea was that instead of saying that things are true or false, then you give them a probability. So there is shades of uncertainty. And then people showed that probabilistic reasoning could capture more patterns of human reasoning than logic could, and so on. And then shortly after that, late 80s, early 90s, came data and machine learning, right? So the thing here was the availability of data. Then we start having web browsers. And a lot of the machine learning was based on probabilistic reasoning and other frameworks. So that went on until basically about 5-7 years ago, when the era of a neural network came in, and basically had a really massive success. And the interesting thing is neural networks have been around since the very beginning, right? So what happened that really popped them to the forefront in terms of applications, we could now optimize them at levels that we could not do before. In fact, the term deep learning comes from that. People couldn't train deep neural networks before, and of course this was aided by availability of data, massive data and computational power. So So we could actually do things within neural networks that we couldn't do before. Now, with the exponential basically spread of neural network applications, now came limitations. I tell people, if you make progress this fast, you also discover limitations this fast. So if you look recently, people have been discussing broadly issues with neural networks and how far we can go with them. And you hear particular complaints about generality. People realize that these sometimes do not generalize well beyond the data. They also talk about the lack of robustness. You probably heard stories and seen studies about where people would build a neural network to recognize stop signs, and then you go put a sticker on the stop sign, and then it will start concluding that it's something else. Sometimes people change the colors of images, and neural networks will change their mind about what they're seeing there, and so on. And something that also received a lot of discussion is explanations and what they call interpretability. So these systems are black boxes generally, and you can see through them. So that drove a lot of the discussions and research recently. And then you realize that almost the calls for a comeback to try to integrate some of the earlier techniques so that to deal with these particular issues. In fact, if you look at two efforts, major funding efforts, one by DARPA from a couple of years ago, where they invested about $2 billion in AI, and you look at the main call for the efforts, you see an emphasis on how we can just go on by simply fitting data, and we need to go and start doing things that resemble more human reasoning and generalize beyond data. And recently NSF, another major funding agency, is spending a few $100 million on building AI centers throughout the nation. And if you look at the call for those centers and their scope, you'll see at the very beginning really positioned statement about AI and about how it's not just machine learning, it's not just neural networks, but everything that you tend to study in an introduction to AI course. Now, to explain some of these things, you have to realize that throughout the history of AI, when people tried various things, there is usually this tendency that when something succeeds, people start saying it is it, right? So when there was logic, it was logic. And when people moved to probabilistic reasoning, it was, is it probabilistic reasoning or logic? And then when machine learning was quite successful, some people were arguing that AI is all machine learning. And recently some were arguing it's all neural networks, we don't need anything else. And all of the recent emphasis is no, we need them all, we need to integrate them. And integration is not as easy for many reasons. Some of them are technical and some of them are more cultural. Typically, these different classes of techniques are pursued by communities that are disjoint. There's also, I refer to educational bottlenecks that stands in the way, because typically people are trained in one of these versus the other. So, well, actually this course is in a sense about integration. And even though it is automated reasoning and the main tools are logical reasoning, you're going to see a major interplay between probabilistic reasoning and logical reasoning and probabilistic reasoning and machine learning. And I'll give you a sense of that in just a second. So in a sense, it is quite unique in that regard. So let me give you a sense now of what we're going to go over. And just before that, let me see if there's anything on the chat here. So the course itself will be, in a sense, have two components, what we would call the foundations. Yes, there's a question.
I got a question from Atharva saying, what does first order logic refer to here?
We'll talk today about Boolean logic, and people will know what that is. First order logic is a more expressive version where you do quantification over objects. It is probably what you have seen. It's kind of the language of math in a sense, even though we will not treat first order logic. We have other courses where that's being treated. We will talk about the relation a little bit, because quite a bit of what happened in first order logic these days are people reduce it to propositional logic and Boolean logic that we'll study in this course. So some of these technicalities will be best answered once we start our technical discussion, because we will answer them in context. There's a question about, does this class assume an intro to AI class? So, okay, I was going to get to this, but let me mention it now. No, this course does not require really background in AI. It requires algorithmic and mathematical maturity. Everything we're going to do here is going to be self-contained. And in fact, the first part, foundational part, is documented in chapters that we'll be posting. I've been writing these as chapters of a book. Okay, let me get again into saying a bit about what the course will be about in terms of discussed material. So it's, you can think of it as two major components. One is the foundations, where we're going to talk about logic, and in particular what we're going to call quantified Boolean logic. So some of you may have seen Boolean logic or propositional logic, and there is this quantification thing where we'll see what it means. It's a little bit step further beyond your classical logic. And then there in that foundational part, we will be talking about some of the really main ingredients in terms of problems and computational engines related to logic. That includes SAT solvers, which have been making a major impact on AI and computer science more generally. You'll get to know how these things work. You can even build one. We'll talk about subjects like tractable circuits. This is going to be very important for us. Which is more modern stuff that happened over the last couple of decades, a particular way of doing logical reasoning and logical manipulations by compiling knowledge into certain type of circuits that are known as tractable circuits. They look like neural networks in the sense that they can be evaluated in linear time. Those going to be actually the link to probabilistic reasoning and machine learning. They're going to play a major role on that, and other related things like max SAT, which are optimization versions of SAT, and so on. So this is the foundation. This is where you get to know syntax, semantics, and become an expert on the core things in logical reasoning. And as I said, a lot of this is documented in book chapters that we will be distributing. So the material is available almost like, undergraduate textbook material. So people who are new to this will hopefully be very comfortable in, building a solid foundation there. And then we're going to get into applications. And that's partly intermingled with the course, but more towards the second part of it. And there we will basically look at, we'll categorize this into, if you want to think about them, three categories. I've been recently referring to these as, the three modern roles of logic in AI. And I'm going to outline them here. And of course, we're going to say a lot about that later. One is logic for computation. And let me actually lay them out all, and then I'll say a few words about each one of them. So in short, and for the first category, which is logic for computation, we're going to approach this from a very systematic point of view. If you look at complexity theory, it tries to categorize problems in different classes or complexity classes. So there is the class NP, which many of you know about, captures many interesting problems, have been, deserved a lot of attention. There is a bigger class known as PP, which captures probabilistic reasoning. And then we're going to look at two more classes, what we're going to call NP to PP, which is NP with a PP oracle, and yet the bigger class that is PP to the PP. Okay, don't be scared by these. They're actually pretty intuitive complexity classes. We're going to go over them later. But the bottom line is, if you look at something like probabilistic reasoning, you're going to find, and machine learning, you're going to find quite a bit of problems, and we're going to look at actually 4 classes of them that are complete for these classes. So in probabilistic reasoning, if you're trying to compute the probability of an event, this would be here. If you're trying to do value of information, like you have a classifier, let's say based on probabilistic reasoning, and then you did not observe all of the features, and you want to know, is it worth getting more features before you get a decision? And you're trying to evaluate the value of features that end up being here. And then what we're going to see is the prototypical problems for these complexity classes. So for every complexity class, there is one problem that represents it. It is the hardest in that class, and it's the kind of the simplest version of, or very simple kind of version of problems in that class. You're going to see that all of the problems that are complete for these complex classes, they're all on Boolean formula. They're all logical reasoning. So the idea is that if you know how to solve these problems, you really know how to solve the other problems through reductions. And this is not just a theoretical exercise. This is actually very practical. So when we study logic and particular tractable circuits, we're going to see how they allow us to solve problems in these complexity classes in a systematic way. And once we do that, then we can use that to solve problems in machine learning and probabilistic reasoning. And we're going to go over this. So we're going to see that symbolic manipulations, and what we're going to study in logic, will give us a systematic framework for solving all of these problems. Really interesting and exciting, especially that the systems that will be based on this will be circuits. This is going to be what we call circuit-based computation. Everything will end up being a circuit, like a neural network, which does these things. And in the second one here, we're going to see a different role for logic, where we're using logic to complement data, right? So intuitively, early systems were based on logic, later systems were based on data. And then if you think about it intuitively, we should be able to learn from both, right? What we know a lot of knowledge through classes, through textbooks, from what our parents, and then we have data from experiences, and then we need to learn from both. Believe it or not, it's not easy. We know how to build systems based on logic. We know how to build systems based on data. Really integrating them in a very profound way is pretty challenging. So we're going to look at this, where you can think of logic as providing constraints that complement data, and we'll see examples there from both supervised and unsupervised learning. In fact, a lot of these things are relatively new. We're even going to look at some more interesting things along another dimension, with how we can basically compile knowledge with data into tensor graphs, so that they can optimize using your classical and neural network-based tools and so on. And in the last category, logic for meta reasoning, or reasoning about the behavior of machine learning systems, this gets to trying to see why are systems doing what they are doing. And here we will look at explanations. You have a system, you give it an instance, and it says, you have an admission system based on some classifier, and you give it an applicant, say, admit that applicant. Say, why did you decide to admit that applicant, right? So explanations. And you're going to see how the stuff we're going to do for the foundations plays a role there. And even questions like robustness, like how robust is the decision, right? How is it easy to change your mind? And even questions relating to bias. Sometimes you have what we call protected features, and then a decision is made, and you want to know, was a protected feature involved in making that particular decision? Very subtle questions. And the main insight there that we're going to be exploiting in that component is that even though your machine learning system, so if you have an ML system or classifier, it's usually used as a classifier. You have what we call an instance, you pass it to the box, and then a decision comes out. So even though these systems are numeric in nature, and even though they're learned from data, they often actually implement discrete functions. So if you're talking, let's say, about admission, you have kind of discrete values for the instance, and the output is admit, not admit. So you can think of the box from an input-output point of view as a discrete function, and therefore you can compile that behavior, the input-output relation, in symbolic form using the techniques that we will study under foundations. And once you're able to compile the behavior of the machine learning system in symbolic form, then you can use the tools that we discussed in the first part to actually do things like explanation robustness and bias and so on. So it's pretty exciting. I have to say that, I've been teaching this course for a while, and the latter part on applications has shifted. So in earlier versions, we would do applications more broader to computer science and not just to AI. And over the last couple of years, the applications have shifted now almost exclusively to AI, in particular machine learning and probabilistic reasoning, due to what's happening today. So that's the overview. Again, it is a course which is kind of an interesting mix of classical AI, probabilistic reasoning, and machine learning, and some computer theory, but all really founded on a very uniform methodology, which is logic and tractable circuits. All right, so let me say a few things about the course logistics. We will be using, as I said, for the first part, it's going to be, you call them lecture notes or chapters that I've been writing. And we already posted a couple of them. It said week 1, but actually that's more than week 1. And then there will be quite a bit of slides, tutorial-like slides based on some of the other lectures in the latter part. We'll share these in a very few occasions. There will be, some papers, but it's mostly written chapters and slides. We will have 4 problem sets, basically about every 2 weeks, and then a midterm and a final. There'll be mostly exercises. The class, in some parts, especially when we start, pretty foundational, pretty almost material that could be some of it at advanced undergraduate. And then we get into some very advanced things. But for the homework and also midterm and final, we'll try to keep it pretty reasonable. At some points in the course, you may feel a little bit, I don't want to say overwhelmed, it's like, wow, this is too much. Don't worry, I mean, just relax. We want to do something comprehensive and useful, and we'll balance that off in terms of load as far as requirements. So basically, if you're doing the homework, attending class, you should be doing fine, right? There shouldn't be any surprises there. And the last thing, again, I wanted to mention, which I had a note, I already answered it, that no AI background is needed, but mathematical and algorithmic maturity, and I think you should be fine. So there's no project. People are asking, is there a project or coding components? No, although we can make some suggestions later for people who are interested in pursuing some of these. There's actually will be plenty of opportunities to either code something or use systems, and in some cases I'll be actually throwing in research problems throughout about things that matter quite a bit. So if one of you develop an interest in something and where doing something would really have an impact in terms of what are the bottlenecks, some of these, for example, relate to the compilation processes of going from logical knowledge to circuits and so on. All right, so let's see. This is all I wanted to say as far as big picture and logistics. And now we're going to go down to earth, start with the foundations of Boolean logic. And some of this, at least what we start with today, some of you have seen. And in general here, we're going to be talking about quantified Boolean logic. So the quantified part will come later. Today, this is not going to come up, but we'll be starting with Boolean logic. And anytime you talk about a logic, there is 2 components. It's what people call the syntax and the semantics. the syntax is effectively what is okay to write, or what are the rules that govern sentences that are written in a logic. And in Boolean logic, it's pretty simple, basically straightforward. We're going to go over this, except that sometimes there are what we call restrictions, or what people call normal forms, which are specific way in which you can express knowledge in a logic. And the notion of normal forms is pretty important for a number of reasons. So what we're going to do is we're going to start with syntax. We'll tell you what are the legitimate sentences in Boolean logic, which will be straightforward. And we'll talk a little bit about a couple of normal forms which are fundamental, okay? Think of these as syntactic restrictions or molds or templates that everybody needs to know. And then semantics is about meaning. If you really want to think about it at a high level, it's what does it mean? So if you write a sentence in logic, what does it mean? What are you saying? And it's important because once you give a formal definition of meaning, of what does a sentence mean, then you can immediately do various things, like talk about the relationship between sentences. Does one imply the other? Is one equivalent to the other? Meaning, are they saying the same thing? Are two things contradictory to each other? Is a statement even consistent? Does it make sense? And we'll see that once we get the basic and essence of meaning, all of these questions will be relatively easy to answer, and you'll actually help me in answering these. So that's what we're going to try to get through today. We have about 8 minutes before our break, so let's get to the syntax part, and then we will tackle semantics when we come back. So with syntax, let's see. So this is syntax. In Boolean logic, it's pretty simple. You start with a set of variables. Let's call them, let's say P1, P2, Pn. And these are variables that could be, you can think of them could be either true or false. So they're binary variables. They are sometimes called propositional variables, or Boolean variables, or atoms, and so on. And the definition of a sentence is pretty simple. PI is a sentence, so any of them is a sentence. And then if alpha, beta are sentences, then the following are sentences: alpha and beta, alpha or beta, not alpha, right? So this guy is the conjunction, the and. This guy is the disjunction operator. It's an or, and this guy is the negation. So if you had these variables, let's say you had a variable A, let's call it, so this is the example, earthquake, and let's say burglary, and this is a alarm. You can write statements like earthquake or burglary happened. You can say not earthquake or not burglary, and so on. Now, there is the other logical connectives like this guy, which is effectively the following. Okay, this may not be as obvious to some of you. Why is this the same as that? But for now, we're going to accept it, and we're going to see that in a little bit. And this guy is simply shorthand for this guy. Right, so these are the connectives you can hear, right? Earthquake or burglary implies alarm, and so on. These are example sentences that you would put there. It's pretty simple. What I'd like to do is mention a couple of terminologies that you need to be aware of. They're very commonly used, and then a couple of syntactic forms or normal forms that are so essential before we take our break. All right, so let's do the first thing I want to mention is some very fundamental terminology. Okay, the notion of a literal. And this is either a variable or the negation of a variable. Okay, they're called literals. So this is called a positive literal, and this is called a negative literal. In a sense, the first one is saying X is true, and the second is saying X is false. The notion of a term and the notion of a clause, I'm gonna write them here. A term is basically a conjunction of literals. So this would be X and not Y and Z and so on. And a clause is a disjunction of literals. So this would be something like not X or not Y or Z or dot, dot, dot. Okay, these are so important. I mean, this is like if you're doing algebra, you're saying a product or a sum, you need to basically know these by heart. Term is a conjunction and a clause is a disjunction of literals. And then we have two normal forms which are pretty important. And the first one of them is conjunctive normal form. And this is CNF. And that's basically a conjunction of clauses. So you may have X or not Y or W and Y or not Z or O or W dot, dot, dot. All right. So these are so this is clause 1 and this is clause 2 and so on. All right, so this is the form. And the last one we're going to talk about for now is basically this disjunctive normal form. And that's known as DNF. Okay, and you can expect what that is. Can someone type the definition? Da of da. Chat box? No? Okay, someone said this would be this junction of terms. Yes, kind of a dual. So this could be something like X and Z or not X and Y and W or dot, dot, dot. So again, what's going on here is we have term 1, term 2, and so on. Okay, now we're going to get to normal forms later. In fact, that's a beefy subject. But let me just mention something quickly here before we go to our break. Conjunctive normal form is so important because a lot of the systems expect the input to be in this form. In fact, set solvers, which have made waves in AI and beyond, actually more generally computer science, these solvers are based on CNF. They want their input to be in CNF. And so if your input is not in CNF, you have to convert to CNF. And the other thing that we should mention about these two particular forms, and something that comes up in when you discuss the restricted forms or normal forms, is whether they are universal Universal means anything can be expressed in that form. So if I tell you I want your input to be in CNF, am I restricting you really? Is there something that you would like to say in logic that cannot be expressed as a CNF? No, right? Anything can be expressed as a CNF. What does that mean? That means that you can take any Boolean sentence and convert it to CNF. And similarly for disjunctive normal form. Disjunctive, if you want to think about it also, from a user point of view, it's easier to express things as conjunctive normal forms because they're pieces of knowledge that are conjoined. The disjunctive normal form usually is used for analysis. If we look at something in disjunctive normal form, we can see through the knowledge and prove certain properties, and we're going to see that actually they play a role in explanations, fundamental role in explanations. Then we get back to these. So I'm going to leave it at this. Someone is asking, are these notes will be shared? Well, the videos will be recorded and shared, and then you have your chapters that this is coming from. So let's take our 10-minute break, and we will resume at 11. Thank you.